Welcome to the Deep Dive, the show that, well, digs into a stack of sources to give you that shortcut to being really well informed.
Yeah, cutting through the noise.
Exactly. And today, we're diving under the hood literally to explore the just incredible complexity of the modern car engine.
It really is something else.
Think of it like a finely tuned orchestra, every single component playing its part in this complex, interconnected symphony of systems.
That's a great analogy.
And we often take it completely for granted, right? Until that dreaded check engine light flicks on.
Yep. The one nobody wants to see.
And this isn't just about simple mechanics anymore. It's about understanding a really sophisticated network, digital, mechanical, constantly communicating its health. If you just know how to listen.
That's right. And our mission today basically is to pull out the critical insights from the ASE A8 Engine Performance Study Guide and some really interesting Bosch diagnostic materials. This deep dive should give you a pretty comprehensive shortcut to understanding engine health, the advanced diagnostic tools technicians are using these days, and the professional standards that kind of underpin the whole automotive industry.
Right.
What's really fascinating, I think, is just how much precision goes into figuring out what seems like a simple check engine light on your dash. It's a marvel of engineering and problem solving, a complex puzzle that skilled pros are solving every day.
Okay, let's unpack this then. Before we even get into the nuts and bolts of performance, we should probably talk about the backbone of automotive excellence, ASE certification. Foundational. For a lot of us, maybe in the past, hiring a mechanic felt a bit like a gamble, right? So why is a non-profit organization focused on auto repair quality so incredibly important? What gap were they trying to fill?
It's a really good question, and it is foundational. Think back maybe before 1972 automotive repair. It was a bit like the Wild West, wasn't it?
Yeah, you just kind of hope for the best.
Exactly. You hoped you found a good mechanic, maybe through word of mouth, but there wasn't really a universal standard, no clear way to measure competence.
Right.
So ASE, that stands for the National Institute for Automotive Service Excellence, they stepped right into that void. They're independent, nonprofit, and their core mission, their whole identity, is super clear. Improve the quality of automotive service and repair, period.
How do they actually do that, though?
Well, they do it by setting these really robust standards and then certifying the automotive professionals who actually meet them.
Okay.
And this benefits everyone. For employers, it means they have qualified staff, competent people, reduces the risk of bad diagnoses, costly redos.
Makes sense.
And for consumers like you, it means more reliable repairs and, honestly, peace of mind. Knowing the person working on your vehicle has actually demonstrated a certain level of skill, verified by an independent body.
It's like a stamp of approval.
Kind of like a good housekeeping seal of approval for mechanics, yeah. And the scale is huge. There are over 400,000 certified professionals out there.
Wow.
Across more than 40 different specialty areas, brakes, electrical, and of course engine performance, which we're talking about today.
So it's pretty widespread.
Oh yeah, its widespread adoption just underscores its role as this universally recognized benchmark. It sets a minimum standard of proficiency, sure, but in reality, it often sets the bar for what people expect from, top-tier technicians. It's really the bedrock of trust in what can be a very technical and, let's face it, sometimes opaque industry.
So building that trust, setting that baseline for quality, absolutely crucial. Okay, let's shift to the how. If ASE is this guardian of trust, how do technicians actually earn that seal? What do they go through to prove they know their stuff? What's actually tested? Is it just simple recall?
No, definitely not simple recall. It's a pretty rigorous process designed by industry experts, people who really know the field, to genuinely challenge a technician's knowledge and their analytical skills.
Okay.
An ASC test usually has somewhere between 40 and 80 multiple choice questions. And these aren't just, dreamed up in an ivory tower.
Right.
They're developed by a real mix of industry veterans, hands-on technicians, educators teaching the next generation, even engineers from the big manufacturers.
So it's relevant to the real world.
Absolutely. That collaboration ensures the tests are highly relevant to what technicians actually face in the shop every day, reflecting current technology.
What kind of questions are we talking about?
Well, there are mainly three types. the most common are probably the direct or completion questions. Pretty straightforward, they just ask for the correct answer to a specific technical point.
Okay, standard multiple choice.
Yeah, but then you have the Technician A and Technician B questions. These are really common, and honestly, they require a deeper level of thinking. It's almost like solving a little mini case study right there in the question.
Yeah.
Wow.
Give me an example.
Sure. Right from the study guide, here's one. A vehicle equipped with rack and pinion steering is having the front end inspected. Technician A says that the inner tie rod ends should be inspected while in their normal run-in G position. Technician B says that if movement is felt between the tie rod stud and the socket while the tie rod is moved in and out, the inner tie rod should be replaced. Who is correct?
Okay, so you have to evaluate both statements.
Exactly.
Oh.
You're not just recalling a fact. You're looking at two different diagnostic statements. Both might sound plausible, and you have to figure out which one, or maybe both, or neither, is actually correct in that specific situation.
And the answer for that one?
In this case, both A and B are actually correct. You should inspect inner tie rods under normal load, and yeah, any movement means it needs replacing. So this format really tests if a technician can evaluate multiple pieces of info and reason through the steps, just like they would in the shop.
Makes sense. What's the third type?
The third type are the accept or least likely questions. These kind of flip the script. They test your understanding by asking you to find the incorrect statement or the least probable cause among the options.
Oh, okay. Tricky.
Yeah, it forces you to think differently, consider all the possibilities, and rule them out systematically. For example, another one from the guide. Blue-gray smoke comes from the exhaust of a vehicle during deceleration. Of the following, which cause is least likely?
Okay. Blue-gray smoke.
Deceleration.
Right. And the answer there would likely be worn piston rings. Because, worn rings usually cause more smoke under acceleration when cylinder pressure is higher, not so much deceleration. It's about knowing those nuances, the subtle relationships between symptoms and causes.
Got it. So how do they actually take the test?
It's all computer-based, now CBT, computer-based testing, which honestly has a lot of advantages for the person taking it.
Like what?
Well, it's super convenient. You can schedule it at a testing center pretty much when it suits you, rather than waiting for one specific test date. Plus, you get immediate scoring. Oh, nice. No waiting around nervously.
Exactly. You know right away if you passed. And if you don't pass, there's a 30-day waiting period before you can retest, which isn't really a penalty. It's more to make sure you actually have time to study up, reinforce the learning.
Makes sense.
Registration is all online through the ASE website, aase.com. Pretty streamlined. And importantly, once you get certified, it's good for 5 years.
5 years? Why not longer?
Because automotive technology changes so fast. Think about it. That 5-year recertification requirement is crucial. It ensures certified techs aren't just coasting on old knowledge. They have to keep updating their skills, stay current with all the new stuff coming out.
Right. Continuous learning. So it's a dynamic, rigorous system.
Okay, for our deep dive today, we're zeroing in on one specific certification, the A8 engine performance.
That's the one. This isn't just about fixing cars in general. This is about mastering the engine's heart, really understanding those complex systems that make it run efficiently and cleanly. What exactly does this A8 test cover? What does its structure tell us about modern engine diagnosis?
The A8 test is designed to really assess a technician's comprehensive grasp of modern engine operation and diagnosis. It reflects just how multifaceted today's vehicles are. The content is broken down into 5 main areas, and each has a specific weighting, which tells you exactly where the emphasis lies. It's all laid out in the study guide.
Okay, break it down for us.
All right. First up, general diagnosis. That accounts for 24% of the questions. This is foundational stuff, accurately interpreting a customer's complaint, translating "my car feels funny" into specific symptoms.
The detective work.
Exactly. Performing initial visual checks, basic performance tests. It's the groundwork before you even plug anything in. Then ignition system diagnosis and repair, that's 16%. This gets into the spark, how it's made, how it's delivered, what goes wrong. Fuel, air induction, and exhaust systems diagnosis and repair makes up 18%. That's the engine's breathing and eating, basically. How air and fuel get in, mix properly, and how the exhaust gets out.
Right.
Emissions control systems diagnosis and repair is another 16%. This acknowledges just how critical these systems are, not just for the environment, but for the engine's overall efficiency in meeting regulations.
And the last one must be the computers.
You got it. The biggest single section, reflecting just how much modern engines rely on tech, is computerized engine controls, diagnosis, and repair. That's 26%.
Over a quarter of the test.
Yeah. This covers the engine's brain and nervous system, the modules, the sensors, the actuators, everything that orchestrates the whole show. So this distribution really highlights the kind of holistic understanding you need. Look at this. General diagnosis and computerized controls together. That's exactly 50% of the test.
Half the battle right there.
Pretty much. It emphasizes that while, mechanical knowledge is still absolutely crucial, the ability to interpret data, understand complex software logic, and perform systematic electronic troubleshooting is equally, if not maybe even more, important on today's vehicles. It's this blend of hands-on mechanics with advanced digital problem solving.
That breakdown really drives home how much there is to know and how integrated it all is. And like you said, it's not always about plugging in the computer first. A good technician starts by really listening first to the customer, then crucially to the car itself.
Absolutely.
This is where it gets really interesting, I think. The engine literally tells you what's wrong, doesn't it?
That's right.
If you know how to listen and interpret its sounds, the subtle ones and the not so subtle ones.
Oh, absolutely. Engine noises are some of the most critical diagnostic clues a technician has. A skilled tech doesn't just hear a noise. They identify its specific character. Is it a tick, a knock, a whine, a rattle? Where is it coming from? Under what conditions does it happen? Idle, acceleration, cold, hot.
Right, the context matters.
Immensely. They develop an ear for these sounds over years. For instance, crankshaft noises. They're very distinctive, usually a deep, dull thump or maybe a heavy metallic knock, typically coming from the bottom end of the engine.
Okay, blow down.
Right. These sounds usually point to problems with the big rotating parts, worn main bearings supporting the crankshaft, maybe connecting rod bearings where the rods meet the crank, issues with the piston pin or wrist pin, or even excessive crankshaft end play.
End play, what's that?
That's the amount of movement the crankshaft has front to back. If you hear a noise specifically when you press the clutch pedal or when the engine is under load, that's a strong hint it might be crankshaft end play noise because that pressure forces the crank to shift. These are serious sounds indicating significant internal wear.
Okay, definitely sounds serious. What about noises from the top?
Right. Moving up top, you get valvetrain noises. These are usually lighter, higher pitched than crank noises, often described as ticking or clicking.
Like a sewing machine sometimes.
Yeah, sometimes like that. These can be traced back to issues like worn rocker arms, maybe a bad rocker arm shaft, problems where the pushrod meets the rocker arm, the ball and seat, or in pushrods themselves, noisy tappets or lifters as they're often called, or even problems with the camshaft lobes or the timing gears and chain.
Lots of moving parts up there.
A ton. And related to that, but distinct, is piston noise. Different from crankshaft noise. It sounds more like a dull or muffled metallic rattle, often called piston slap.
Slap?
Yeah, it signals too much side-to-side movement of the piston in the cylinder bore, usually from wear. Piston pin noise, though, is typically a lighter, higher-pitched tap, often heard only at certain RPMs.
Okay. What about those hydraulic lifters? Are these supposed to be quiet?
Ideally, yes. Hydraulic lifters are designed to automatically adjust to maintain zero valve lash, which prevents noise. But if they aren't working right, they can produce a constant ticking sound. This could be due to a sticking valve stem, preventing the lifter from adjusting, maybe low oil pressure getting to the lifter, or just excessive internal clearance. And sometimes these lifter ticks can be really persistent and hard to get rid of without replacing them.
Any other really bad sounds?
A really concerning one is spark knock, also known as detonation or pre-ignition. It's that sharp metallic ringing or pinging sound, almost like marbles rattling around in a can.
Heard that one before. Not good.
Definitely not good. It means you've got abnormal, uncontrolled combustion happening inside the cylinder, which is incredibly destructive. Yeah. And then there are other general noises, maybe a high-pitched squeal that gets faster with RPM, often a slipping belt, or rattling from a loose bracket. A deep, muffled sound could be an oil pump failing, or maybe just an exhaust leak. Each specific sound, its character, when it happens, it all combines to form a crucial piece of the puzzle, guiding the technician toward the root cause. It really is a symphony of clues.
It truly is amazing how much you can tell just by listening. And you mentioned spark knock, how destructive that is. It's not just about fire inside the engine. It's about controlled fire.
Precisely.
So what exactly happens when that delicate controlled process goes wrong, leading to those noises and, well, much worse problems?
Yeah, the combustion event inside an engine cylinder is meticulously timed and controlled, down to the millisecond. Ideally, what we want is normal combustion. Spark plug fires, the air-fuel mix ignites smoothly, a single controlled flame front sweeps across the combustion chamber, burns all the fuel efficiently. That controlled explosion pushes the piston down, makes power. That's the engine working its design. Smooth, powerful, efficient.
The ideal scenario.
Right. But things can go wrong in really damaging ways. One major issue is pre-ignition. This is when the air-fuel mixture ignites before the spark plug even fires.
How does that happen?
It's often caused by hot spots inside the combustion chamber. Could be excessive carbon buildup on the piston or valves, maybe an incorrect spark plug that gets too hot and acts like a glow plug. These hot spots ignite the mixture too early.
And that's bad because
That uncontrolled explosion happens while the piston might still be traveling upwards on its compression stroke. It creates tremendous pressure before the piston is in the right position, essentially fighting against the engine's rotation. Very damaging.
ouch. Okay, what about detonation? You mentioned that too.
Right. Detonation, or knock, often happens alongside pre-ignition, but it's slightly different. Detonation occurs after the spark plug is fired, but instead of one smooth flame front, you get uncontrolled secondary explosions. Imagine ripples in a pond. Normal combustion is one smooth ripple. Detonation is like dropping multiple stones in randomly, and the waves crash into each other violently.
Creating that rattling sound.
Exactly. That collision of flame fronts creates shock waves, causing that distinctive metallic pinging or rattling common causes. Using low-octane fuel that isn't resistant enough to ignition, those same hotspots or carbon buildup, an overly lean air-fuel mixture which burns hotter, ignition timing that's too far advanced, sparking too early, or even problems with the EGR system, the exhaust gas recirculation system, which is supposed to help cool combustion.
So, multiple potential causes.
Yeah. And both pre-ignition and detonation are extremely harmful. They generate excessive cylinder pressures and intense localized heat. Over time, this uncontrolled force can lead to severe damage: cracked pistons, bent connecting rods, burned valves, damaged bearings. It can fundamentally wreck an engine if it's not addressed.
So, very delicate balance. Precision is absolutely key. Okay, beyond the sounds, you mentioned the exhaust tells a powerful story too.
It does.
What visual signals, specifically coming out the tailpipe, should you look for? What do the colors, maybe even the smells, reveal?
Right beyond the sounds, the exhaust is like a direct report from inside the engine. The color, even the smell of the smoke are significant diagnostic clues. Vital signs, really.
Okay, like what? Let's start with black smoke.
Black smoke is a classic sign of an excessively rich air-fuel mixture. Basically, too much fuel for the amount of air or not enough air getting in. The engine's running fat.
What causes that?
Could be a range of things. Something simple, like a really clogged air filter restricting airflow. Or maybe a restricted exhaust system, like a blocked catalytic converter, preventing gases from getting out efficiently. More complex stuff could be faulty fuel injectors stuck open, dumping too much fuel. Maybe fuel pressure is too high because of a bad regulator. Or even inaccurate sensor readings like the oxygen sensor or MAF sensor telling the computer the wrong thing, tricking it into adding too much fuel.
And you can usually smell that, right? Like unburnt gas.
Oh, yeah. Usually comes with a strong gasoline odor. Now, excessive white smoke, that's a different story and usually more concerning.
Fair.
This is a clear sign that engine coolant is getting into the combustion chambers and burning. You have to distinguish it from normal condensation you see on a cold morning, which disappears quickly.
Right, this is persistent smoke.
Persistent, thick white smoke. Often smells kind of sweet, too. That's the ethylene glycol in the coolant. This almost always points to a serious internal breach. Cracked cylinder head, maybe a cracked engine block, or the most common culprit, a blown head gasket. Coolant seeps in, burns, turns into steam, needs immediate attention.
Definitely sounds serious. What about blue smoke?
Blue-gray smoke specifically signals that engine oil is burning. Oil is getting into the combustion chamber somehow.
How does that happen?
Most common causes are worn piston rings that aren't sealing against the cylinder walls anymore, letting oil sneak up from the crankcase. Could also be worn valve guides or bad valve stem seals, allowing oil to leak down from the cylinder head past the valves. Or even a malfunctioning PCV system pulling too much oil vapor into the intake.
And that has a distinct smell, too.
Yep, usually a pungent, acrid smell of burning oil. So yeah, beyond just smoke color, unusual smells like fuel or burning oil, or even unusual sounds like a rattling catalytic converter, these are all vital clues. They paint a pretty comprehensive picture for a sharp technician.
It's really incredible how many different senses a technician needs to use. It's like being a detective.
It really is a lot of observation.
Okay, now let's talk about the specialized tools that help confirm these suspicions and uncover problems you can't necessarily see or hear directly. Some look pretty simple, but they can tell you a surprising amount. Let's start with the humble vacuum gauge. Looks basic, right?
Deceptively basic, yeah. The vacuum gauge is incredibly powerful and versatile, often underestimated. You connect it to the intake manifold, usually there's a specific port, or you tap into a main vacuum line. It measures the engine's manifold vacuum.
Which is,
Basically, the suction created by the pistons drawing air during the intake stroke. A healthy, efficient engine pulls a strong, steady vacuum. And different readings, different needle behaviors on that gauge give you this quick, real-time snapshot of engine health. Can pinpoint a whole array of issues without even plugging in a scan tool yet.
okay, so what's a good reading look like?
On a healthy engine at idle, you're looking for a steady needle, typically somewhere between 17 and 22 inches of mercury in JOT-HG. Nice and stable.
And when it's not steady?
That's where the diagnostics really begin. If you see an intermittent fluctuation at idle, the needle kind of drops or jumps occasionally, that might suggest sticking valves or maybe an ignition miss in one cylinder, like a little hiccup.
Okay. What if it's steady but low, like below 17?
A low reading, say 15 to 20, but still steady. That could point to a general loss of efficiency, maybe late ignition timing or late valve timing across the board. Could be uniformly low compression in all cylinders, maybe a throttle valve stuck slightly open. Or, very commonly, vacuum leaks could be at the carburetor base, throttle body gasket, or intake manifold gaskets letting unmetered air sneak in.
What about a drifting needle?
If the needle is drifting slowly, irregularly, often points to improper carburetor adjustment on older cars, or maybe just a general issue with the intake manifold sealing.
And if it fluctuates when you rev the engine?
Right. If the needle fluctuates as engine speed increases, that's a classic sign of weak valve springs struggling to keep up, or maybe worn valve guides allowing flutter, or even a vibrating cylinder head gasket. Points to dynamic issues that show up under load or speed.
Interesting. Any other patterns?
Yeah, a couple more key ones. A gradual drop in reading at idle, and the reading gets even lower as RPM increases. That's your classic sign of an exhaust restriction, a choked muffler, or a plugged catalytic converter backing things up.
Okay, back pressure.
Exactly. And finally, if the needle vibrates excessively at idle, but then smooths out as engine speed increases, that often points specifically to worn valve guides causing turbulence at low speeds. One important thing, though, you always have to correct for altitude.
Altitude. Why?
Because atmospheric pressure drops as you go higher, so engine vacuum will naturally be lower. The rule of thumb is you subtract about 1 inch of mercury from the expected reading for every 1,000 feet you were above sea level. So yeah, this one simple gauge gives you this incredibly powerful, immediate window into the engine's breathing and sealing.
That's a surprising amount of info from one needle. Okay, but what if you suspect something more serious internally, deep inside, like worn rings or a bad valve? What tests do techs turn to then to really nail down the problem?
For those deeper internal mechanical issues, 2 tests are absolutely essential: the compression test and the cylinder leakage test.
Okay, compression test first. What's that involve?
A compression test measures the maximum pressure each cylinder can generate during its compression stroke. You pull out all the spark plugs, disable the ignition and fuel system so the engine won't start, and then you crank the engine over. A special gauge screwed into the spark plug hole measures the peak pressure built up in each cylinder.
And you compare the readings.
Exactly. The goal is consistency. If one cylinder reads significantly lower than the other, say 20% or more below the average, that strongly indicates a problem in that specific cylinder.
But how do you know if it's rings or valves causing the low reading?
Great question. That's where the wet compression test comes in. After you get the low-dry reading on a cylinder, you squirt a small amount of engine oil, maybe a teaspoon or so, into that cylinder through the spark plug hole. Then you repeat the compression test on that cylinder.
What does the oil do?
The oil temporarily helps seal the gaps around the piston rings. So if the compression reading significantly improves after adding oil, it strongly suggests worn piston rings are the culprit. The oil filled the gap.
And if it doesn't improve?
If the reading stays low or doesn't improve much even with the oil, that points towards a valve issue, like a burned valve, a valve stuck open, maybe even a blown head gasket, because oil won't really seal a leaking valve or a head gasket breach effectively.
Clever. Okay, what about the cylinder leakage test? How's that different?
The cylinder leakage test, or a leak down test, takes it a step further. Instead of measuring pressure built by the engine, you introduce compressed air into the cylinder from an external source, like the shop's air compressor. You bring the piston in the suspect's cylinder up to top dead center, TDC, on its compression stroke, so both intake and exhaust valves should be closed. Then you feed in compressed air through a special tool in the spark plug hole. The tool has two gauges. One shows the pressure going in, the other shows how much pressure the cylinder is holding, indicating the percentage of leakage.
But the real key is listening, right?
Exactly. While the air is going in, you listen carefully to find where it's escaping. If you hear air hissing out the exhaust pipe, leaking exhaust valve, hear it hissing back through the intake manifold or throttle body, leaking intake valve, hear it hissing out the oil filler cap or the PCV valve opening, that's air blowing past worn piston rings into the crankcase.
Wow.
And if you hear bubbling in the radiator or coolant reservoir, or maybe air escaping from an adjacent spark plug hole, that's a telltale sign of a blown head gasket letting air cross into the cooling system or the next cylinder. These two tests, compression and leakage, especially when used together, give you a remarkably precise diagnosis of internal engine sealing problems. Saves a ton of guesswork.
It's incredible precision. Okay, so from hands-on gauges and careful listening, we now shift firmly into the digital realm. Technology has just completely revolutionized diagnostics, hasn't it?
Oh, absolutely. Night and day difference.
Giving technicians this unprecedented access. Let's talk scan tools and onboard diagnostics to OBD2. How have these tools changed the game, making the invisible visible?
Yeah, OBD2, which came about in the mid-90s, was an absolute game changer. Before that, every car manufacturer had their own proprietary diagnostic systems, different codes, different connectors.
Yep.
It was a nightmare for independent shops.
Right. Needed a different tool for every car brand.
Pretty much. OBD2 standardized everything, the way vehicles monitor their emissions and performance, the diagnostic connector, the basic code structure. It made diagnostics way more accessible and consistent across the board.
And at the heart of it is the car's computer.
Exactly. The powertrain control module, or PCM, sometimes called the engine control module, ECM, that's the central brain. It controls almost everything engine-related. Fuel injection, ignition timing, emissions components, often the transmission, too.
Okay. And how do you talk to this brain?
Through the data link connector, or DLC. That's the standardized 16-pin port, usually under the dash on the driver's side. Any compatible scan tool can plug into that DLC and communicate directly with the vehicle's computer network.
And when something goes wrong, the computer knows.
Yeah, the PCM is constantly monitoring sensors and actuators. If it detects a malfunction, say a sensor reading that's way out of its expected range, or an actuator like an injector not responding correctly, it sets a diagnostic trouble code, or DTC.
Those are the check engine light codes people hear about.
Exactly, like a P0172 means fuel system too rich. These DTCs are standardized codes that quickly tell a technician the general area, P for powertrain, B for body, C for chassis, U for network, the specific system, whether it's a generic or manufacturer-specific code, and then a definition of the fault. So P0172 means the same basic thing on a Ford or a Toyota.
Okay, so the scan tool reads the code. What else can it do? They seem pretty sophisticated now.
Oh, they've come a long way beyond just reading codes. A key function is viewing freeze frame data. This is incredibly valuable. It's a snapshot of all the relevant sensor readings, engine RPM, coolant temp, vehicle speed, fuel trims, engine load recorded at the exact moment the fault occurred and the DTC was set.
Like a black box recorder for your car's fault.
Exactly. It provides crucial context, helps you understand the conditions under which the problem happened. Then there's a live data streams. This shows you sensor readings in real time as the engine is running. You can watch RPM, coolant temp, O2 sensor voltage switching back and forth, MAP sensor readings changing with throttle, and critically, fuel trims.
Fuel trims, you mentioned those before, STFT and LTFT.
Right, short-term fuel trim, STFT, and long-term fuel trim, LTFT. Think of STFT as the PCM's immediate, tiny adjustments to fuel delivery, reacting instantly to the O2 sensor feedback, trying to keep that air-fuel ratio perfect. LTFT is more like the learned adjustment. If the PCM consistently has to add fuel, positive LTFT, it learns this over time and applies a baseline correction. High LTFT often points to a persistent underlying issue, like a vacuum leak making the engine run lean, forcing the computer to compensate long term.
So you can see the engine adapting in real time.
Precisely. And modern professional scan tools, like the Bosch ones mentioned in our materials, go even further. They offer bidirectional controls,
Yeah.
meaning the technician can use the scan tool to actually command certain components to turn on or off for testing. You can command the cooling fans on, pulse the EVFP purge solenoid, command the fuel pump relay on, sometimes even perform cylinder contribution tests electronically.
So you can test parts without even touching them.
In many cases, yes. It speeds up diagnosis hugely. These Pro Tools often have OEM-level coverage, meaning they can access almost as much data and perform almost as many functions as the dealer's factory tool. They let you truly interact with the car's digital brain, not just listen to it.
That's a massive leap. Okay, so the scan tool talks to the computer, but sometimes you need to see the actual electrical signals themselves,
Right.
especially for tricky intermittent problems.
Exactly.
That's where the oscilloscope comes in, giving technicians like X-ray vision into the electrical heartbeat.
That's a perfect way to put it. An oscilloscope, or scope, is absolutely indispensable. It displays electrical signals visually as waveforms on a screen, plotting voltage against time. Unlike a multimeter that just gives you a single number for voltage or resistance at one instant.
The scope shows you the whole picture changing over time.
Precisely. It shows the shape, the frequency, the amplitude, the timing of that electrical signal. This is absolutely critical for diagnosing intermittent problems that might only happen for a fraction of a second, or for looking at complex dynamic signals that change rapidly, stuff a multimeter just cannot capture. Trying to diagnose a complex electrical issue with just a multimeter is like trying to diagnose a heart rhythm problem by just taking someone's pulse rate. The scope is the EKG.
Makes sense. What kind of things do techs use it for?
Oh, tons of stuff. A huge application is analyzing ignition system patterns. A scope can show you the secondary ignition waveform for each cylinder firing. You look at the firing voltage spike, the duration and voltage of the spark line itself, the coil oscillations afterwards.
And deviations mean problems.
Big time. A really high firing voltage spike might mean high resistance, like a worn plug or wide gap. A really short spike might mean low compression or a fouled plug. A spark line that slopes downwards indicates high resistance during the spark. If the oscillations after the spark are weak or missing, it might point to a shorted coil winding. You can literally see misfires, crossfiring between cylinders, lean mixtures affecting the burn time. It's incredibly revealing.
Wow. Beyond ignition.
Absolutely. Scopes are vital for analyzing sensor signals. You can watch the O2 sensor signal switching smoothly between rich and lean. You can look at the output of a MAP sensor or MAF sensor to see if it responds correctly and smoothly as the engine load changes. You can check the square wave output from crank and cam sensors for glitches or dropouts. You can even look at the command signals going to actuators like fuel injectors to verify the PCM is sending the right signal. It lets you see those invisible electrical pulses and diagnose dynamic timing-related issues that no other tool can reliably catch. It turns guesswork into visual confirmation.
So scan tool tells you the what and the conditions. Scope tells you the why by showing the electrical reality.
Okay, one more major diagnostic tool. Analyzing the exhaust gases themselves. You said it's like a full health report. How does that work? What does it tell you beyond just pass or fail on an emissions test?
Yeah, exhaust gas analysis gives you incredibly deep insights into how efficiently the engine is actually burning its fuel and how well the emission systems, especially the catalytic converter, are doing their job. An exhaust gas analyzer, typically a 4-gas or 5-gas analyzer, measures the concentration of key gases right in the tailpipe.
What gases are key?
Usually hydrocarbons, HC, carbon monoxide, CO, carbon dioxide, CO2, oxygen O2, and sometimes nitrogen oxides.
And what do they tell you?
They tell you about combustion efficiency. The ultimate goal is that perfect stoichiometric air-fuel ratio, 14.7 parts air to 1 part fuel. At that ratio, you get the most complete combustion, and crucially, the catalytic converter works best. Deviations show up immediately in the gas readings.
Like the black smoke we talked about earlier. Exactly. If you see high HC, hydrocarbons, that's unburned fuel coming out the pipe, often caused by ignition misfires, maybe valve sealing issues, or a very rich mixture, just raw fuel escaping.
Okay. What about CO, though?
High CO, carbon monoxide, means incomplete combustion. There wasn't enough oxygen to burn the fuel fully into CO2 and water. This almost always points to an overly rich mixture. The engine is starving for air or getting way too much fuel.
Makes sense. What about NOx?
High NOx, nitrogen oxides, typically indicates excessively high combustion temperatures. Remember, NOx forms when temps get really hot, above 2,500 degrees F or so. This can be caused by a lean mixture, which burns hotter, ignition timing being too advanced, or the EGR system not working properly to cool things down.
And O2. Shouldn't there be very little oxygen left after combustion?
Ideally, yes, very little O2 in the exhaust. If you see high O2, it usually means one of two things. Either the engine is running lean, too much air went in for the fuel provided, or there's an exhaust leak before the sensor, sucking in outside air and fooling the analyzer, and the car's own O2 sensors.
And you can use this to check the catalytic converter, too.
Absolutely. A key diagnostic technique is to measure the gases before the catalytic converter, if possible, and then after. A healthy converter should dramatically reduce HC, CO, and anox levels. If the readings are almost the same before and after, or the after readings are still very high, it's a strong sign the converter isn't doing its job. It might be worn out, contaminated, or physically damaged. So yeah, that gas analysis provides this invaluable, immediate report card on the entire combustion and emission control process.
Okay, we've covered the general approach, the toolkit. Now let's dive deeper into the core systems themselves, starting with the one that kicks it all off, the ignition system. It's more than just spark plugs, right? A lot more going on there to get that precisely timed spark.
Oh yeah, way more. The ignition system is literally the spark of life. Its whole job is to deliver a very high voltage spark to each cylinder at exactly the right microsecond to ignite the fuel-air mixture. It works using two circuits, primary and secondary.
Primary and secondary. How does that work?
The primary circuit is the low voltage side. It starts with the battery, goes through the ignition switch, then to the primary windings of the ignition coil, which is basically a step-up transformer. The engine's computer, or points in very old systems, rapidly switches this primary circuit on and off.
That does what?
Every time that primary circuit current is suddenly switched off, the magnetic field built up in the coil collapses violently. This collapse induces a massive voltage, tens of thousands of volts, in the coil's secondary windings.
Stepping up the voltage.
Massively. That super high voltage is then directed out through the secondary circuit, either through heavily insulated spark plug wires to the plugs, or in newer systems, directly through a coil sitting right on top of the plug.
And then the spark plug does its thing.
Right. That high voltage jumps the gap between the spark plug's electrodes, creating the spark that ignites the mixture. Systems have evolved, though. Old cars had a single coil and a mechanical distributor to send the spark to the right cylinder.
Right, cap and rotor.
Then came distributorless ignition DI systems, often using coil packs that fire pairs of cylinders. And now, most common is coil-on-plug, where each spark plug gets its own dedicated ignition coil right on top. Super precise timing control.
So what goes wrong? What are the common symptoms of ignition problems?
All sorts of things. A complete no start or a hard start is a big one. No spark, no fire. More common might be an engine misfire, where one or more cylinders aren't firing correctly. You'll feel that as rough running, shaking, lack of power.
Check engine light flashing, probably.
Often, yeah, especially if it's a persistent misfire. That also leads to poor fuel mileage because you're wasting fuel. And sometimes incorrect timing can cause spark knock or detonation, which we talked about being really damaging.
So how do you diagnose these? Visual checks first.
Always start with the basics. Visual inspection. Pull the spark plugs. What do they look like? Are they worn? Is the gap right? Are they fouled with carbon, oil, or deposits? Are the insulators cracked? Look at the spark plug wires. Any cracks, burns, corrosion on the terminals. On older systems, check the distributor cap and rotor for cracks, carbon tracking between terminals, corrosion.
What about the more advanced stuff? Scope again.
Absolutely. The oscilloscope is king for ignition diagnostics. Analyzing those secondary waveforms we discussed, firing voltage, spark line, burn time, coil oscillations, each pattern tells a story. High kV spike, maybe lean mixture or wide gap. Low kV, fouled plug, low compression, sloping spark line, high resistance, weak oscillations, coil issue. You can see it all, cylinder by cylinder.
Beyond the scope.
Component testing. Test the ignition switch itself. Test the ignition coils. Check the resistance of both primary and secondary windings against specifications. On systems that use them, test pickup coils or Hall effect sensors. These are the sensors that tell the computer the crankshaft or camshaft position, which is critical for timing. You check the resistance or voltage signals.
And analyzing the spark plugs themselves gives clues too, right?
Oh, huge clues. Spark plug analysis is like reading tea leaves, but for engines. The condition of the plug tip tells you so much about what's happening in that specific cylinder.
Like him.
Well, if the gap is bridged with deposits, the spark can't jump. Oil fouled, plugs black. Oily deposits point to oil burning. maybe bad rings or valve seals. Carbon-fouled, dry, black, sooty deposits usually means a rich mixture or weak spark, incomplete combustion.
What about plugs that look burnt?
Right, signs of pre-ignition or overheating, melted electrodes, blistered insulators, maybe chalky white deposits that tells you the cylinder is running way too hot. Could be a lean mixture, timing too advanced, cooling system problems. Each look tells a specific story, guiding you to the root cause in that cylinder.
Amazing detail from such a small part.
Okay.
Moving on, the engine needs spark, but it also needs the right mix of fuel and air. That's the next critical system. Fuel, air induction, and exhaust. Getting that perfect blend determines performance, efficiency, everything. How does that all work?
You got it. Precision in fuel and air is absolutely paramount. Let's trace the fuel first, the fuel delivery system. It's the whole journey from the gas tank to the engine.
Pump, filter, lines.
Yep. Usually an electric fuel pump, most often inside the tank these days, and tank pump. Then a fuel filter to catch dirt and debris, really important for protecting the injectors. Fuel lines carry the fuel under pressure. And a fuel pressure regulator maintains a consistent pressure for the injectors, ensuring they deliver the right amount.
Got to be careful working on that stuff, right?
Yes.
High pressure, flammable.
Absolutely. Safety first, always. You always relieve the fuel system pressure before disconnecting anything. Diagnostics involve checking fuel pressure and volume. Is the pump delivering enough fuel at the right pressure? Low pressure or volume causes hesitation, stalling, poor power, especially when you demand more from the engine.
Then the fuel gets injected.
Right, into the engine via fuel injection. We've moved way beyond carburetors. Most engines use manifold injection spraying fuel into the intake port just before the valve. Or, increasingly common, gasoline direct injection, GDI, where fuel is sprayed directly into the combustion chamber at extremely high pressures.
And the computer controls this.
The PCM controls it with incredible precision based on all those sensor inputs. And this is where those fuel trims, STFT and LTFT, are constantly working. They're the PCM's way of using oxygen sensor feedback to fine-tune the fuel injector pulse width, making tiny adjustments constantly to keep that air-fuel ratio right at the ideal 14.7.1 mark for best efficiency and emissions. Watching fuel trims on a scan tool is a key diagnostic step.
So if an injector itself is bad, how do you test that?
Several ways for fuel injector testing. You can check the electrical resistance of the injector's coil. You can use a scope with a current probe to look at the electrical current pattern as it operates that can reveal electrical or mechanical issues inside the injector. And you can do a fuel injector balance test.
Balance test.
Yeah, you measure how much fuel each injector flows in a set amount of time. This identifies injectors that are weak, not flowing enough, or maybe leaking or clogged, causing imbalances between cylinders which lead to misfires and rough running.
Okay, that covers fuel. What about the air side? The breathing?
Right, the air induction system starts with the air filter, then usually the throttle body. This has a throttle plate, or butterfly valve, that opens and closes to control how much air enters the engine. Modern cars use electronic throttle control drive-by-wire, no cable from your pedal.
So the computer controls the throttle plate?
Yep, based on your pedal input and other factors. The throttle body also houses sensors like the throttle position TP sensor, telling the PCM how far open the throttle is, and often an idle air control, IAC, valve, or motor, which lets a small amount of air bypass the throttle plate to control idle speed smoothly.
Measuring the air.
That's crucial. Usually done by a mass airflow, MAF sensor, typically located between the air filter and throttle body. It measures the mass of air flowing into the engine, which is more accurate than just volume because air density changes with temperature and altitude. There's also usually an intake air temperature, IAT sensor. The PCM uses these MAF and IAT signals, along with others like MAP, manifold absolute pressure, to calculate exactly how much air is entering, so it can determine precisely how much fuel to inject.
And some engines get help breathing. Turbos and superchargers.
Right, forced induction. Turbochargers, driven by exhaust gas, and superchargers, driven by the engine belts, are essentially air compressors. They force more air into the cylinders than the engine could suck in naturally. More air means you can burn more fuel, which means more power.
But more complexity, more things to go wrong.
Definitely adds complexity. Common issues with turbos, for instance, include oil leaks. They spin incredibly fast and get very hot, so lubrication is critical. Bearing failures can happen. And problems with the wastegate, the valve that controls how much exhaust bypasses the turbine to regulate boost pressure. If the wastegate sticks open, you get no boost. If it sticks closed, you can get way too much boost, which is dangerous. Diagnosing these requires understanding how the whole boost control system works.
So intricate systems for fuel and air, and then equally complex these days are the emissions controls. People think of them maybe just for passing tests, but you see
What?
they're vital for engine health too.
Absolutely vital. Modern emissions controls are deeply integrated. They don't just clean up the exhaust, they often help the engine run better and last longer. Take the positive crankcase ventilation, or PCV system.
Okay, PCV, what's that do?
During combustion, some gases inevitably blow past the piston rings into the crankcase below. These are called blow-by gases, unburned fuel, exhaust, moisture. Without a PCV system, this pressure would build up, blow out seals, contaminate the engine oil, turning it acidic and sludgy. Bad news.
So the PCV valve.
The PCV system uses engine vacuum to draw these blow-by gases out of the crankcase through the PCV valve, which controls the flow, and routes them back into the intake manifold to be burned in the engine. So it relieves pressure, keeps the oil cleaner, and burns those stray vapors. Simple, but crucial. A stuck PCV valve can cause oil consumption, leaks, or rough idle.
Okay, what about EGR? Exhaust gas recirculation. It sounds counterintuitive putting exhaust back in.
It does sound weird, but it's ingenious. EGR systems are primarily there to reduce nitrogen oxides, NOxes, those smog-forming pollutants created at very high combustion temperatures.
How does putting exhaust back in help?
The EGR valve introduces a small, precisely controlled amount of inert exhaust gas back into the intake air entering the cylinders. This exhaust gas doesn't burn, but it takes up space and absorbs heat. This effectively lowers the peak combustion temperature, keeping it below the point where NOx readily forms, around 2,500 degrees Fair.
Clever.
Yeah. There are different types of EGR valves, vacuum-operated, electronic ones, pressure feedback types. The PCM controls when and how much EGR flows, usually under cruising conditions, not at idle or full throttle. Problems. Clogged EGR passages are common, or the valve itself fails. Symptoms can be spark knock, because combustion temps get too high without EGR, rough idle, hesitation, or even stalling if the valve sticks open.
Got it. What about secondary air injection? Pumping air into the exhaust.
Right, the AR system. This is mainly used during cold starts. When the engine is cold, it runs rich, meaning there's extra unburned fuel, hydrocarbons, HC, and carbon monoxide, CO, in the exhaust. The AR system pumps fresh air directly into the exhaust manifold or near the catalytic converter. That extra oxygen helps burn off, oxidize, that excess HC and CO in the exhaust stream itself. It also helps the catalytic converter heat up faster, light off, so it can start working effectively much sooner after a cold start. Issues usually involve the air pump failing or the check valve sticking.
And the star of the emissions show the catalytic converter.
Definitely the centerpiece.
Yeah.
It's this amazing chemical reactor. Inside is a honeycomb structure, usually ceramic, coated with tiny amounts of precious metals, platinum, palladium, rhodium.
And these metals do the work.
They act as catalysts. As the hot exhaust flows through, these metals trigger chemical reactions that convert the three main harmful pollutants. LOX gets broken down into harmless nitrogen and oxygen. HC and CO get oxidized into less harmful carbon dioxide, CO2, and water, H2O.
How do you know if it's working?
Best way is with that exhaust gas analyzer we talked about, comparing readings before and after the converter. A working converter should show a huge drop in HC and CO, and also convert NOx efficiently under the right conditions. If it fails, gets clogged, contaminated, example by coolant or oil, or physically damaged, it can cause a major exhaust restriction, leading to low power, bad fuel economy, and definitely a check engine light.
Okay, one more EVAP systems. Evaporative emissions. That's about fuel vapors.
Exactly. Gasoline evaporates easily, creating fuel vapors. The evaporative emissions EVAP system is designed to capture these vapors from the fuel tank and lines, preventing them from escaping into the atmosphere, which is a big source of smog-forming pollution.
How does it capture them?
It's a sealed system. Vapors from the tank are routed to a charcoal canister, which acts like a sponge, absorbing and storing the fuel vapors when the engine is off.
Then what happens to them?
When the engine is running and conditions are right, not usually right after refueling or at idle, the PCM commands a purge valve to open. This allows engine vacuum to draw the stored vapors from the canister into the intake manifold, where they get burned along with the regular air-fuel mixture. There's also a vent valve that seals the system for testing or opens to allow air in when needed.
And check engine lights for this, even a loose gas cap.
Absolutely. The PCM runs sophisticated self-tests on the EVIP system, looking for leaks. It might pressurize or pull a vacuum on the system and monitor if it holds. Even a tiny leak, like from a loose or faulty gas cap, can fail the test and trigger the check engine light. Diagnosing EVAP leaks often requires a special smoke machine to pump smoke into the system and visually find the leak, or using a scan tool to monitor the pressure sensor and command the valves to check their operation. So yeah, all these systems work together, constantly monitored, to keep things clean and efficient.
It really is astounding. So many layers of control, all working behind the scenes. And this brings us to the conductor of the whole orchestra, the brain, the PCM or ECM, and its huge network of sensors and actuators. This is where everything we've discussed comes together, isn't it?
Absolutely. The powertrain control module, PCM, or engine control module, ECM, is the central computer, the absolute nerve center. It's constantly monitoring dozens of inputs from sensors all over the engine and vehicle. It processes this data incredibly fast using complex algorithms, and then sends precise commands out to the actuators, the parts that actually do things, to optimize performance, minimize emissions, maximize fuel economy, everything.
It's a constant feedback loop.
A continuous high-speed feedback loop. Sensors measure conditions, PCM processes, actuators respond, sensors measure the new conditions, repeat. Thousands of times per second sometimes. It allows the engine to adapt instantly to changing conditions, load, speed, temperature, altitude, fuel quality, you name it.
Let's talk about some of the most critical sensors feeding it information. What are the key players?
Okay, some absolutely vital key sensors. The oxygen sensor, O2S or HO2S for heated O2 sensor, is a huge one. Usually there's at least one before the catalytic converter and one after. They measure the amount of oxygen left in the exhaust gas. This tells the PCM if the air-fuel mixture was rich, too much fuel, little O2 left, or lean, too much air, lots of O2 left. The signal from the front O2 sensor is the primary feedback for those fuel trim adjustments we talked about.
Okay. What about telling the engine where it is in its cycle?
That's the job of the camshaft position sensor, CMP, and the crankshaft position sensor, CKP. The CKP is usually the primary sensor for ignition timing and fuel injection synchronization. It tells the PCM exactly how fast the engine is spinning, RPM, and the precise rotational position of the crankshaft. The CMP sensor tells the PCM which specific cylinder is on its power stroke, which is needed for sequential fuel injection, and on many systems for identifying misfires. Lose the CKP signal. The engine usually won't run at all.
Yeah, essential. What else?
Many others. The intake air temperature, IAT sensor, measures the temp of the air coming in. The manifold absolute pressure, MAP sensor, measures pressure or vacuum in the intake manifold, which is a key indicator of engine load. The mass airflow, MAF sensor, as we mentioned, measures the mass of air entering. The throttle position, TP sensor, tells the PCM how far you've pressed the gas pedal. Engine coolant temperature, ECT sensor, is critical for adjusting fuel mixture, idle speed, and fan operation based on whether the engine is cold or hot. And the vehicle speed sensor, VSS, provides road speed data used for various things like cruise control, transmission shifting, and even idle control.
That's a lot of data points.
And that's just some of the main ones. The PCM takes all these inputs and uses them to control the actuators. These are the parts that make things happen.
Right.
Like the ignition coils firing the spark plugs, the fuel injectors opening and closing, the idle air control valve adjusting idle speed, the EGR valve opening, the EVB purge valve pulsing, the cooling fans turning on, the electronic throttle plate moving. The list goes on.
And if something goes wrong with a sensor or actuator, that's the DTC again.
Exactly. If a sensor signal is missing, or irrational, way out of expected range, or if the PCM commands an actuator and doesn't see the expected result, maybe through feedback from another sensor, it sets a diagnostic trouble code. And again, the scan tool is your window into this, reading codes, looking at that freeze frame data context, and monitoring the OBD2 monitors. Yeah, these are self-tests the PCM runs on various systems. Some run continuously, like misfire detection and fuel system monitoring. Others, called non-continuous monitors, only run when specific driving conditions are met. Tests for the catalyst, EGR system, O2 sensors, EVAP system. The scan tool can tell you if these monitors have completed their tests since the last time codes were cleared, which is important for diagnostics and emissions testing.
And you still need your basic electrical skills too, right? Multimeters and stuff.
Oh, absolutely essential. Electrical testing with a good digital multimeter DMM is fundamental. You're constantly checking for proper voltage supply to sensors and modules, checking sensor signal voltages, measuring resistance of components like coils or sensors, testing for continuity in wires, or checking for shorts to ground or power. Sometimes a problem is just a bad wire or corroded connection, and that might not set a specific code, but it definitely affects how things work.
What if the PCM itself is the problem?
It happens, though, less often than sensor or wiring issues. But if the PCM ECM needs replacement, it's usually not just a simple swap. Often the new module needs initialization and reprogramming. You have to load the correct software for that specific vehicle model and VIN, sometimes configure options, and often perform procedures to link it to the vehicle's anti-theft or immobilizer system so the car will actually start with the new brain.
Complex. And all these computers talk to each other now, too.
Yeah, that's the final piece of the puzzle, vehicle communication systems. Modern cars don't just have a PCM. They have modules for the transmission, ABS brakes, airbags, body controls, infotainment, dozens sometimes. They all need to share information efficiently. They do this over high-speed data networks, most commonly the Controller Area Network, or CAN bus. Think of it as the car's internal internet. This allows modules to share sensor data and coordinate actions. But it also means a problem on the network, or with one module, can sometimes affect communication with others, adding another layer to diagnostics.
Wow, okay. That's an incredibly detailed picture of just how sophisticated these engine systems are, from the sounds and smells right down to the digital pulses on the CAN bus. So how does a technician actually put all this knowledge together in the real world? Let's try putting on our tech hats for a second. Can you walk us through maybe a sample test question connected back to what we've discussed, show how that theory turns into practice?
Yeah, absolutely. This is where it all connects. These ASE-style questions really test that synthesis of knowledge and diagnostic reasoning. Let's grab one from the study guide, page 89, question 1. It sets up a scenario. After the compression readings shown above were taken, a wet compression test was made. The second set of readings was almost the same as the first. Technician A says that a burned valve could cause these readings. Technician B says that a worn piston ring could cause these readings. Who is right?
Okay, so we have low compression, and the wet test didn't help much.
Exactly. Now think back to our discussion on compression tests. What do we say the wet test helps differentiate?
If the compression comes up with oil, it's likely rings. If it doesn't come up, it's likely valves.
Perfect. So in this case, the readings were almost the same, meaning the oil didn't seal the leak. That points away from rings and strongly towards a valve sealing issue like a burned valve.
So technician A is right, B is wrong.
Precisely. The answer is technician A only. See how it directly tests your understanding of that specific diagnostic procedure and how to interpret the results? It's not just knowing what a compression test is, it's knowing what the results mean in context.
Makes perfect sense. Got another one.
Sure, let's look at question 3, same page. A vacuum gauge is connected to the intake manifold of an engine running at 2,000 RPM. During the test, the pointer on the gauge fluctuates rapidly between readings of 10 and 22 inches of vacuum. These test results point to A, a leaking intake manifold gasket, B, worn piston rings, C, worn valve guides, D, a weak or broken valve spring.
Okay, vacuum gauge fluctuating rapidly, wide range, and at 2,000 RPM, not just idle.
Right. Now recall our vacuum gauge diagnosis chat. What kind of reading was associated with rapid fluctuations, especially as RPM increases?
That sounded like a valve train issue, maybe? Something dynamic happening with the valves?
You got it. A leaking intake gasket usually gives a low, steady reading. Worn rings may be a low reading or a flutter that diminishes with speed. Worn valve guides, often more vibration at idle that smooths out. But that wide, rapid fluctuation, especially off idle, is a classic symptom of a valve not seating properly or consistently at speed, often caused by weak or broken valve springs. Answer D, that can't control the valve's motion correctly at higher RPMs.
So again, connecting the specific reading pattern to the most likely underlying mechanical cause.
Exactly. These questions really emphasize that it's not just about memorizing facts in isolation. It's about critical thinking, applying the knowledge, understanding the relationships between symptoms, test results, and the underlying systems. That's what makes a good diagnostic technician.
It absolutely does. And that brings us back to that bigger picture you mentioned, the sheer interconnectedness of it all.
It's fundamental. Engine performance today isn't about separate, siloed components. It's this incredibly complex, choreographed dance. Mechanical parts, ignition, fuel, emissions controls, the computer network, they all have to work together in perfect harmony, dynamically adjusting all the time.
And a fault in one place can ripple outwards.
Oh, absolutely. It cascades. A simple example. A failing oxygen sensor gives bad data to the PCM. The PCM then calculates the wrong air-fuel mixture, maybe too rich. That rich mixture causes incomplete combustion, leading to maybe misfires, ignition system symptom, definitely higher emissions, emission system impact. And over time, that rich mixture can overheat and destroy the catalytic converter downstream. One sensor failure triggers a chain reaction across multiple systems.
So you can't just treat the symptom.
You really can't. You have to take a holistic approach, understand those interdependencies. Otherwise, you're just chasing symptoms, replacing parts that might fail again because the root cause wasn't addressed. Like replacing that cat converter without fixing the rich mixture condition that killed it in the first place. That comprehensive view is absolutely key to efficient, accurate, lasting repairs, seeing the whole forest, not just individual trees.
This whole deep dive has really highlighted the complexity, the ingenuity,
Yeah.
but also the constant evolution. And it makes you wonder, what's next? What does the future hold for automotive diagnostics as cars get even more complex, more software-driven, maybe electric?
The future is already arriving, and it's evolving incredibly fast. The Bosch materials we looked at hint at this, tools moving way beyond just reading codes. We're seeing diagnostic platforms offering incredibly deep live data, extensive bidirectional controls, even reprogramming capabilities becoming more common in aftermarket tools.
And electric vehicles change everything, right?
Completely different ballgame in many ways. EVs bring whole new systems, high voltage batteries, electric motors, complex power inverters, regenerative braking. Technicians need entirely new skill sets, different safety protocols, different diagnostic tools focusing on high voltage systems, battery health management, software diagnostics for motor controllers.
What about ASE? All the driver assistance features.
Another huge area. Advanced driver assistance systems, adaptive cruise, lane keeping, auto braking rely on cameras, radar, LiDAR sensors. After many common repairs, like windshield replacement or even just wheel alignment, these systems often need precise recalibration. This requires specialized ADAS calibration equipment targets, lasers, sophisticated software to ensure those safety systems function correctly. Millimeter accuracy matters.
And AI. Is that coming to the diagnostics?
It's definitely starting to play a role. Imagine diagnostic systems using AI and machine learning. They could analyze massive amounts of vehicle data from connected cars, potentially identify patterns that predict failures before they happen, true predictive maintenance. AI could also assist technicians by suggesting the most probable diagnostic paths based on symptoms and historical data from millions of vehicles. Remote diagnostics is also growing the car, sending data directly to a service center for analysis.
So the job itself is changing drastically.
Profoundly. As vehicles become more like rolling computers, software-driven, connected, electrified, eventually more autonomous, the role of the diagnostic technician evolves. It's shifting further from purely mechanical skills towards software updates, network troubleshooting, data analysis, calibration procedures, understanding complex system interactions across the entire vehicle network. Continuous learning isn't just important, it's the absolute baseline requirement to stay relevant in this field. The demand for skilled technicians who can master this evolving technology is only going to grow.
What an incredible journey today. From the basics of ASE certification to the intricacies of CAN bus networks and the future of AI and diagnostics. We've covered engine noises, exhaust smoke signals, vacuum gauges, scopes, scan tools. It really gives you a new appreciation for what's happening under the hood every time you drive. Hopefully some real aha moments for you listening.
And it just underscores that constant innovation means this deep dive into understanding vehicles is really a never-ending journey. Every smooth ride relies on this invisible network of incredibly complex systems and the highly skilled professionals who keep them running right. There's always more to learn, and that critical thinking, sorting through the information, is just essential, especially with these amazing machines we rely on every day.
Absolutely. Well, thank you for joining us on this deep dive into engine performance and diagnostics. We hope you feel much more informed, maybe even a little awed by the complexity. Join us next time for another deep dive into a fascinating topic.